Okay, we are about to go into recording, which I will cut out eventually, but just be aware of it in case you say anything.
Yeah, okay. So what we have here is guys and well, guys and gals, doing teletype from all. There's one. There we go. So those little two tones that are going back and forth, called diddling, actually create a line of type, and you could read out call signs and everything else. So this is just another part of the hobby. A lot of people get really interested, and this is one of the worldwide contests. Unfortunately, conditions aren't amazing. They're marginal at best. I'm hearing into Europe and I'm hearing into Russia. And the guy we're listening to right now is VE5MX in Saskatchewan, I think. 5, yeah. Anyway, that's just a little demonstration, Emma, of something else in ham radio. Back to you, Rod. And I'll turn my audio down.
Okay, very good. So everybody mute. I'm about to turn it over to John any second now. John, if you want to, actually don't quite screen share yet. I'll do a quick introduction for you. Hold on. I just need to put speaker up here. Gosh, all this fun. So good morning, Cycle 25 for September 25th. I'm lucky to have John, VE6EY. And John, what are you here to talk about today?
Well, I'm here to talk about diversity reception. One of our group asked a few weeks ago if I could do a presentation on it. And I was kind of busy during the summer getting a new floor put in. So I put it off to September, and it's now September. So I'm all set to go, Rod.
Okay, go ahead and share your screen. This should be another good one. And I think you also mentioned something about a demo at the end, which should be kind of cool.
Yeah, we'll do a demo at the end of my new radio, which I just got. Okay.
I can see the slides. They look good.
You can see the slides. They look good. Okay, here we go. Diversity reception. What is it? How does it work? And I promise you all one thing, I'm not going to do any math today. So this is going to be a math-free presentation. But if you really want to get into this stuff, you will have to learn some math a bit later. Okay. So let's talk about fading. I think all of us have a concept of what fading is, but consider one of those signals Peter was just listening to. It's maybe taking a 5,000 kilometer path on 20 meters coming to your house. In actual fact, there is not one single path that a signal takes. It takes multiple paths. It gets bounced off the ionosphere in different ways. It might reflect off water, mountains, or buildings. So you might get a whole bunch of copies of the same signal arriving at your antenna at roughly the same time. So if you think about a 5,000 kilometer path that takes multiple routes to get to your home, the odds are good that one path might be, say, 10 meters longer than another path when two copies of signal arrive. And when they arrive, if there's a difference in the path length of 10 meters, which is about a very small percentage of the distance, guess what? Those two copies of the signal will be 180 degrees out of phase. Now, what happens when two copies of the signal are 180 degrees out of phase? Well, they tend to cancel. So this is my simple definition of short fading or multipath effects on HF. Signals take multiple paths to get to your single antenna. They arrive slightly different, and they tend to cancel each other. So the question then arose back in many years ago, maybe 100 years ago, what would happen if we had two or more spaced receive antennas? So back in 1936, some guys named McLaughlin and Lamb, who were the sort of QST technical gurus, found out from doing a lot of study that signals don't fade identically in two antennas at the same time. And they tend to be diversified. The fading is different, and statistically, you can actually combine the signals and get a better quality that offsets some of the random fading that's taking place between multiple paths. And in their own words, diversity reception is the method which takes advantage of this vulnerable spot in fading's armor. So if you're looking at the screen, you can see the effects of fading in the lower left, and you can see what's causing it in the upper left. So there's the concept that got everything started. How do we compensate for multipath fading? So the answer is diversity reception. And I don't know, Mark, if you can see the screen, but I promised you you'd be getting a starring role in this presentation. And if you can see the screen, this is it.
It's your 30 seconds of fame, Mark.
And if you can't, Mark,
I'm waiting for this my entire life, John. I've been training for this. I'm good to go. Thank you.
Okay, so let's think about a single transmitter sending out signals into the ionosphere that are taking multiple paths. They're identical signals, but they're taking different paths. Let's say we have two signal chains. Each signal chain is one antenna and one receiver. And these antennas could be different antennas or similar antennas, or they could be close together or far together. But the point is, you can take these two signals and combine them and offset some of the effects of fading. How do you combine them? Well, you can do it analog. Back in the day, this was all done with taking the signal after the product detector and using the AGC from each signal to control the output based on the strongest signal that was being received. So that's an analog way of doing it. Today, we do it digitally, where we take the IQ data stream down at baseband and do mathematics on it and get the same kind of effect. Or we can do human diversity combining, which is basically wearing a pair of stereo headphones with one signal chain in each ear and letting your brain sort of figure out which is best. And most ham radio manufacturers seem to think the human technique is the superior one because that's basically all they're offering. And we'll get back to that later. So with diversity reception, you're really getting two different effects. And I want to talk about each of these because they're similar but different. So part of what you're getting is array gain, where basically if you have two antennas spaced apart and each is getting an identical copy of the signal at a slightly different time, this could be due to antenna phasing or antenna spacing, whatever. You get beamforming from this effect by constructively combining to create lobes or destructively combining to get nulls in the array pattern. And what array gain does is it increases the average signal to noise ratio. And I have the word deterministic at the top because it's assuming the copies of the signal coming through each chain are identical, just at a slightly different time. So array gain does nothing to compensate for fading. It just lets you create different patterns between the two antennas to improve signals, okay? The second effect is the diversity gain, which is a statistical or stochastic process. It assumes arrival of randomly different copies of the signal due to multipath. So in other words, the signals are not identical. They're randomly varying because they're getting affected differently by the ionosphere. Some are stronger, some are weaker. So if you have a single antenna, then these different signals will combine destructively or constructively, and that gives you fading in a single antenna. But if you have two or more receive chains, you can actually mitigate these effects. And diversity gain is a statistical method that lets you combine the different signals to improve the probability of the best signal to noise ratio. So antenna gain is deterministic. It's very simple. There's no stats. Diversity gain is stochastic. So these are similar but different. The array gain is coherent addition of signals and non-coherent averaging of noise. Directional signal to noise improvements will arrive for both fading and non-fading signals, but you're basically doing beamforming, okay? Diversity gain only applies to fading channels. It changes the slope of the probability distribution of the signal to noise ratio. That's the most math I'm going to give you today. And you get improvements by combining independent copies of the signal for best results. So both array and diversity gain can be achieved together with multiple antenna elements and receiver channels. And this is generally what we refer to today as diversity reception. It's not pure diversity gain, it's a combination of array gain and diversity gain, okay? So types and methods, types of diversity, you probably all know this, but I'll cover them anyway. I've been talking mostly about space diversity, which is where you have spacing of your antennas. You could also have antennas which are polarized differently. You might have one that's vertical and one that's horizontal polarization, because as you know, HF signals rotate as they travel through the ionosphere. You can have angle of arrival diversity. You can have frequency diversity, which is where you're listening to two stations on two different frequencies and combining them later. And that was done a lot during World War II. And then you have time diversity as well, which is where you can record something at different times. Now, all of this stuff was really important in the early days of HF, especially around the World War II period, because you were trying to send radio teletype, Morse code, shortwave broadcasting, and get the best signal through. Now, there's a bunch of combining methods, which I'm not going to cover, but you can select, you can do equal gain, or you can do maximal ratio combining. And this chart here basically shows that depending on which algorithm you choose, you get the best gain as you add elements to your array. And as you choose the different algorithms, you get best gain for maximal ratio. And for example, that's why SDR Play in their RSPduo chose the maximal ratio combining for their two channels. Now, you're not going to get much more than 3 dB of diversity gain with two channels, but you are getting some. So beamforming is something different. You know, I've talked a lot about interference calculation in the past. With the array gain, you can focus on the left, as you can see here, on increasing the lobe towards the signal and getting a stronger signal to noise ratio. Or on the right, you can see you can actually create a null in your beamformer to null out the interference and get a stronger SNR because there's less interference, right? And there again, this is how the ANC4 and all these other devices work in the analog world. And this is what I do a lot of in my diversity gain, because I want to reduce interference from RFI. How is this all done? Well, on the left, you can see how it's done analog. So basically, you've got a number of antennas. You can adjust the amplitude and change the phase of the signal coming from each antenna, sum them together, and that gives you an array gain. Or you can just have your multiple antennas with coherent oscillators and sampling clocks, and you can get everything down to baseband and do the same mathematics digitally with your IQ signals at baseband. And that's the way things are being done today. So I know this is kind of technical, so let's go back and look at history. It all started in 1926 with a guy named Beveridge. At RCA, he invented space diversity after extensive study of how signals fade. And along the way, he invented automatic volume control, which was the technique he used to select between the best and the weaker signals for diversity reception. So there's a long history, almost a century of history to diversity reception. During the 1930s, Hallicrafters brought out their DD1. And what was special about this is it was a single control tuning, one oscillator for multiple receivers. I know it looks like on the screen there's two big dials. The one on the left is the main, and the one on the right is band spread. So there's not actually two different receiver dials. There's just one, but it's divided the way they used to do back in the old days between main and band spread. And this became the standard for for simple dynamic range approaches. If you bought that today, it would cost you $8,000. Single control tuning, like here's the schematic from that 1936 QST article. And these are tubes, by the way. You've got a single control that adjusts your pre-selector and the oscillator over on the left side. And then you've got a mixing of your AVC going to the final amplifiers before the detector, and you can combine the AVC. So this gives you a single control tuning, 2-channel receiver with diversity reception. Now today you can get the same thing for $280 in real money. This is the RSPduo, basically 2 receivers you can see on the left, a single coherent oscillator, and 2 1.5 megahertz channels that you can then play with and mix together at baseband. So in a nutshell, diversity reception, you get 2 receivers, 2 antennas. Each of the receivers has fading at a different time. You combine them together, and the top blue line that you can see shows a better signal to noise ratio because you're using the best signal to control the receiver. That in a nutshell is diversity reception. This was very common, like I said, during World War II. Here's a picture of a rack of RCA AR88 receivers used for triple diversity for a long, long time. Okay, here's my diversity reception system. I've got an array of 2 wideband loops, 100 feet along the side of my lot. And I can mix these 2 together to create patterns for beamforming and antenna steering. Or I can mix one of the loops with my HF antennas. I've got a dipole for 40 meters and a tri-beam up on a tower. That's the system I use. I get all the way from broadcast band up through about 10 megahertz. I can create pretty good patterns with the loop array system. Because signals arrive at different times at each loop, I can phase them and I can create beams and I can get rid of all kinds of noise. You can see at the bottom, if I shift the pattern to block my noisy neighbor to the west, I can pretty much get rid of it. So my DR system performance combines everything we've been talking about. I get amazing ability to reduce RFI across all of HF through null steering. I get a very good steerable directional patterns below 15 megahertz with beamforming, either with the loop array or I can combine a little bit with the ham antennas. And I do get diversity reception across HF and MF, but quite frankly, it's the noise reduction that makes the biggest difference rather than controlling the fading. So my almost final thoughts are, we focused on HF medium frequencies today, but all of these techniques work across the entire spectrum, from audio to microwaves, even light. On the wireless front, all of these techniques and more are used in multiple input, multiple output devices. And we've skipped all the math today. We've talked about that before. So that's my primer. If you want to dig into the math, you've really got to figure out how to work that formula on the left, which basically says we're going to apply a bunch of weights to each channel. The weights are going to vary amplitude and the phase of each channel and get the signals to add constructively or destructively, and we get improvements. So ham radio options. Looking at the market today, what I call the higher end radios, not the top of the top, but the higher end radios like you got from shown here from Yaesu, Hallicrafters, ICOM, Flex, and Anan. They're all diversity receivers. They're all called diversity receivers. Why? Because they've got 2 independent receivers, in most cases with the same bandpass filters and performance specs. And you can do diversity reception with 2 antennas at the same time. Only one of these lets you mix the signals at baseband to do what I truly want to do in terms of diversity reception, and that's the Anan radios from Apache Labs. Any of the rest of these, they don't even provide IQ, separate IQ paths to your computer. So like Hallicrafters says it might in a future firmware update do that. ICOM gives you IQ data, but only 1 channel at a time. So, you know, if you want to do diversity reception with the mark picture, with a pair of headphones, all of these will do it for you. If you want to do it the way I do it, with controlling the phasing and math at the baseband, only the Apache Labs will do it for you.
So the Flex should be able to give you I and Q out on multiple, I'm assuming that's a VE600 with the multiple capture units so that you could be
Yes.
receiving from multiple antennas at a time.
Yeah, and they could easily do that because they're all Vita 49 time-stamped and everything. And all of these rigs, including the Flex, could easily be sending its IQ data either to the FPGA to do manipulation on board and then use a thin pipe to your computer, or they can use the fat pipe to your computer and let you add on diversity reception, but they don't.
Interesting. Well, okay. Does it need to have a coherent local oscillator for that to be usable?
If you want to do the math at baseband, yes. If you just want to listen with your headphones, no.
Okay, good point.
Yeah, if you want to do the math, and by the way, all of these are coherent, right? They all have it. You can sync together the oscillators in all these radios, but only one of them actually gives you the baseband manipulation, and that's through the Power SDR software, which I find really frustrating. But anyway,
John, I'm fascinated when you're mentioning this being used in World War II and yet appearing in a article in QST in 1936, which is pretty awesome that a civilian hobbyist magazine has got an article out there saying, hey, this is really cool, this is really useful, and then, gosh, the military picks it up and runs with it.
Yeah, well, keep in mind, a lot of this stuff was coming from RCA and Hallicrafters, who were also big military producers. But the original experimenting started commercially with beverage at RCA. It got picked up by Lamb and McLaughlin in the 30s, more in the hobby world. There was some hams in Mexico that actually built a number of receivers as well. And then, of course, the shortwave broadcasters picked it up. They used it for CW. They couldn't mix together the tones properly for CW or teletype, but they created mechanical relay things to take the tones and sort of regenerate the tones. So anything for long distance telecom, they were using this for telephone circuits across the Atlantic. I mean, it was just used all over the place. Why it hasn't become more popular in terms of ham radio and getting rid of local noise is my total frustration, but I can't do anything about it, so I just carry on.
So I've got an ICOM 2820, which is a D-Star unit, so VHF, UHF unit, and it's got a diversity receive port on the back of it. And now I want to go look at those schematics and see what they're actually doing.
Yeah, they're probably giving you audio from two different receivers, but I have no idea. I'm not familiar with that.
Yeah, it does require two antennas on the vehicle, which has solved a whole problem for me for a while when there weren't that many D-Star repeaters in Toronto here. But it's interesting to see that application, or at least that title being used, whether it's the same technology or not.
You know, it could be doing beamforming, which is another form of diversity reception, because if you look at all the home routers with two antennas, they're actually doing beamforming to try to fix the problem of local multipath around the home. All of the cell towers, the cellular, they use MIMO. They take diversity reception because multipath is a big problem for VHF and UHF in urban areas, right?
Right.
Hey, Rod.
Yes.
Yeah.
Right.
Let me just add one little asterisk on the Flex deal. I've been directly involved in negotiating contracts with military and universities. And I can't say for certain this is the case, but Flex gets pounded. Why don't you do X? Why don't you do Y? Whereas a non kind of sort of doesn't have any restrictions by R&D being funded by the military. You know, it's an open source deal from the get-go with commercialization by a company. Okay. So I don't know this that I can say publicly, but I'm going to throw out a strong suspicion that Flex is dragging their feet is not technological, the lack of technological work. It is the ability to make it public based upon their military R&D. Remember, we only have the 6000 series rigs from Flex because of a prior military contract.
So I appreciate what you're saying, and that makes me reinforce, I don't mean to be in any way critical of any of these manufacturers, especially Flex Radio. I have one, it's great. But I would point out that the essence of Apache Labs diversity reception is Power SDR software, which was created originally by Flex Radio. And with the early Flex radios, you could actually do diversity reception in some of their models way back when, before the Signature series, using Power SDR. So I appreciate what you're saying, Frank. I think it's more a failure to recognize in a modern urban environment the ability to reduce interference. I think that's more of the issue. And please, Mr. Flex, if you're listening, no means critical. It's just, I wanted to buy before I die a really good diversity receiver, 16-bit ADC. And I went looking. I was prepared to buy any one of these, but I ended up buying this one.
And John, I didn't take your comment as being critical. And there's only so much I can say, but I'm just saying that is a retarding factor. And how important is it for them to do it? Now, let me say also from the publisher's endpoint, my former employer, where I was editor-in-chief, Springer, has published between 12 and 20 books on beamforming in the last 5 years. That's a metric of the science and engineering that's going into it. So you are truly spot on in what you're seeing. And I'll just kind of end there, just throwing that in just to amplify what was being said.
And John, can so I've got my Flex 6600 here. I can easily run two receivers at the same time, one in my left ear, one in my right ear, different antennas. Sorry, I got somebody kicking off in the other radio here. And I take it that that's not the ideal diverse reception scenario you're talking about. Is that correct? I'm trying to get up to speed here on just what.
Go ahead. In terms of pure diversity reception, getting diversity gain to combat fading, what you're basically doing is the same thing McLaughlin and Lamb were doing back in the 1930s. You're picking out the best audio signal post-detection, and your brain is figuring out which is the better quality.
Right.
And yeah, that is pure diversity reception. Are you doing any kind of beamforming to reduce noise or steer a null or whatever? No. For that, you actually need to in the modern radios, get down and manipulate the IQ data at baseband. So you're only getting part of the solution, right?
Okay. I think I understand what you say right up to the time we get to IQ data, because I do have IQ data here, and I've used it with the CW skimmer, having everything run and then have IQ data going to the CW skimmer. So that's as much as I understand.
Okay, well, basically the simple thing is here. Just let me pop ahead.
Yep.
This is the Anand 7000 block diagram. Here's the rig. So for the rig, you've got 3 antenna connectors for your main antenna and 1 RX2 over on the right for your second receive chain.
Yep.
So on my setup here, I've got my main ham antennas going into ANT1. I've got one of my loops going into ANT3, and I've got my other loop going into RX2. So when I'm tuning across the bands, I can choose either single antenna, the ham antenna, or I can do diversity with either antenna 3 and with my 2 loops together.
Yep.
What this does is the receiver has, and all of the receivers we showed previously, they have duplicated RF filters, attenuation, AD converter, and down conversion. And they send some data to your software. Now, in the case of the Anand, it's a fat pipe. It's not as advanced as the Flex, so they're sending smaller amounts of bandwidth. Once it gets to my Thetis software, which is a new version of Power SDR, I can either do receiver 1, receiver 2, or I can mix them together.
Right.
And by mixing them together, that simply means I'm taking the data, which is channel 1 data, channel 2 data, and I'm manipulating the amplitude and phase of that data to create beams with the 2 antennas, to reduce fading effects, all the kind of stuff I've been talking about. Okay.
So that data is not audio. That's a digital data. You're in the digital realm doing that manipulation. Is that, am I understanding that correctly?
Right. It's baseband RF data that's been sampled and down converted down to baseband. It's called an analytic pair.
Okay.
And generally called IQ data. But that's basically the radio signal being received by your A to D converter. It's converted to this data.
Okay, now I understand a lot more. Thank you, John. Appreciate it.
Yeah, and because I can do that manipulation before the rest of the receiver chain, I can actually apply the noise blankers, notch filters, equalizers, all that kind of stuff to the data after I've created the diversity and beamforming effects. Right.
Okay.
And all of this is really not hard to do, but you got to get those synchronized streams of IQ data somehow into the software. Or you could do it in the FPGA and the Flex if they gave you a diversity control knob.
Okay.
But they don't. And I just spent $28 and waited 16 weeks for this darn thing to arrive from India. Because I wanted to play with the best that I could play with while I'm still alive. And this was all I could find.
Yeah. Yeah.
Nice.
Yeah, that makes a lot of sense. I really appreciate it. It's funny that you would talk with this guy. I just bought a low noise headphone amplifier, which is pretty much end game. And from my digital streamer, I turned off its DAC. I'm going into my own DAC and then into this amplifier into $1,900 headphones. And so I'm kind of understanding what realm we're in here, sort of what field we're in here. I'm just finding it fascinating. And I agree with you on the diversity receiver for the Flex. I'll talk to Flex directly through Mike, and we'll see what he says. But that's really interesting. Really interesting.
Yeah, so it's not like I've abandoned my Flex. It's still sitting here. But
Yeah.
here's the Anan. I'm just going to give you a quick demonstration. I'm running longer than. Am I okay, Rod?
Yeah, no, you're great.
Yeah.
This is fantastic. Let's
Great.
get on to the demo. This is awesome.
Okay, so I can't figure out. I can't figure out how to share my diversity at the same time here. Just, I got to stop doing this for a sec.
Okay.
I need to.
While you're setting up, I'm going to share with the group that last time we did something like this, we were listening to some music out of the Middle East, and we actually got a YouTube takedown order as a result. But hopefully it's all audio. We'll be okay this time.
Okay, so can you hear me over the background?
Yeah, no, this is great. The balance is good.
Okay, so here's this is probably Cuba or something on 11860. This is my noise band with the neighbor's halogen lights. Here is the west loop antenna. Here is the east loop antenna. You can see there's still a signal there, but about 20 dB of more noise.
Yep.
Here's diversity reception. Okay, antenna 1, antenna 2, antennas combined.
Wow.
John, you could have reduced your entire talk to just these last 4 seconds.
Yeah. So, I mean, okay, now this is a worst case situation. I can also switch over very easily to my beam versus one loop. Here's the beam on the tower, stronger signal, but still lots of noise.
Yeah.
Here's the reference loop on the east side of the tower. And I'll have to adjust the combining. I'm sorry I can't show you that at the same time. I can't figure out how to get it to show. Or maybe it is showing, I don't know. I can get it better, but there we go. The beamforming really works best if you have identical antennas in an array like I have with my loops.
So what are you using for loops, John?
So these are wideband LZ1AQ 0 to 30 megahertz loops, 1 meter loops, amplified.
Yeah.
Yeah.
Oh, okay. And so how are you protecting them when you're transmitting it? You're obviously switching them out of the line.
So I've actually had a long conversation with the creator of these amplifiers, and he says as long as I'm just running a couple hundred watts and I'm 50 feet away, there's enough headroom not to damage them.
Oh, okay.
So so I've done it with the beam antenna because there's good vertical spacing, not so much with the inverted V. You know, so anyway, this is the demonstration that it really does work amazingly. And can you see the phasing control, Rod?
Yeah. Well,
is this showing up?
No, you're not. No, we're not. I saw it on your video that you posted to YouTube the other day. The kind of the circular thing that you're dragging around, the vector that you're dragging around.
That's right. Unfortunately, it's a separate window, and I can either share the receiver or I can share the phasing control. So I thought the receiver might be more interesting. But anyway, that's my demonstration. I'm going to do some videos. So with this receiver, I'm just going to kill the audio here, just in case we have a problem. With this receiver and the signal chain, this is my best receiver for medium wave DXing. I can do amazing things, and there's enough headroom. I just tuck in about 20 dB of attenuation just to protect myself from the nearby powerhouses. But it works great. I can do east-west beamforming with my end-fire array, and I can pick up a station from Dauphin, and then I can switch to the west and pick up a station from Vancouver, all on the same frequency. So this is really good for that. For shortwave reception, Anana's done a pretty good job of building the shortwave bands in here. You've got to be careful in terms of which pre-selector gets selected, because all the pre-selector and stuff is done based on the ham band. So you have to know a little bit about that. But it works really well, $2,800. You know, I didn't want to spend this much. Now, I'll be really, really honest here. I did a comparison on this same band with All India Radio at 1400 in the morning. All India Radio coming in 13,000 kilometers with the RSPduo versus this. And the RSPduo actually sounded better at $280.
Wow.
It does a great job. The signal strength and the SNR weren't as good, but their audio is just amazing in the SCR Uno software, whatever. So I'm posting that on my blog because I was actually super impressed. You don't need to spend $2,800 for HF. The RSPduo will do a pretty good job, but not on AM broadcast band and not on the lower ham bands, because you need the decent band pass filtering for that, or else you just get all sorts of artifacts from AM broadcast. So I've gone longer than I should have. I'm stopping the share. There we go.
Okay, well, thank you, John. As always, you knocked it out of the park, my friend. I'm going to stop the YouTube recording now, and if there's any informal questions, we'll follow with that.